Hi, I'm Philip, a second year PhD student with the CCIMI, and today I'll be presenting a quick video on hyperspectral image classification. So I'm going to split this into two parts. Firstly, we'll look at image classification, where a given input image is transformed into an output classification label. Secondly, we'll look at hyperspectral imaging, how that relates to the electromagnetic spectrum, and how it differs from standard colour images. Let's look at the task of image classification. So given a set of images and a set of possible classes, we seek to find a function f of x, which maps each image onto the correct classification label. So in this problem, we have the animal kingdom, and we seek to find a function f, which can identify different species of different animals. Often though, you might want to associate more than one label with an image. So here the function f of m can associate multiple labels with one image. How do we design such functions? Well, firstly, we should choose a model with 3 parameters we can change. Secondly, we're going to update those parameters using machine learning, where we learn from labeled examples which we'll call our training data. So we feed a training data, i.e. an image and a label, into our model. And our model, initially poor, will produce an incorrect guess, a lion. But we know, in this case, the correct output should have been a dog. And we can backpropagate this error into our model and update our parameters. And we will do this several hundreds of thousands of times for differing training data. We now need to think, when should we stop? And often this involves a validation training set, and there are several clever methods to do so. After we've stopped training, we can then test our model on a testing set to evaluate our performance. Let's now look at hyperspectral images. So we can denote that colour is incredibly important for a lot of machine learning image classification tasks. And let's look at an example. So here we seek to design a fruit classifier. So it takes in a given image of a fruit and produces a classification label. From the colours, it seems like a very easy task. However, if we go to a black and white world, we see that we've lost a lot of information. So the apple and the orange now look similar, and we'd have to rely on more complicated features, such as texture features or shape features. A much harder challenge. So we've seen that if we lose colour, we make our job a lot harder in a lot of machine learning tasks. But now we can go the other way. Even though we only see in RGB, we're not limited to using those colours in a machine learning framework. In fact, we have the entire electromagnetic spectrum available to us, and we could sample in any number of those spectral bands. And this is what hyperspectral images seek to do. They sample hundreds of spectral bands, so instead of just being RGB, you produce a huge spectrum for each pixel. And this spectrum contains very discriminative information, and it allows us to start classifying on a pixel by pixel basis, rather than classifying over the entire image, which you could never do on an RGB colour basis. To see the power of hyperspectral imaging, here's an example. There's a farm in California from satellite data. From an RGB perspective, it would be impossible to name which crop is which, or to work out how many different types of crops. But we know there are 16 different labels, so there's 16 different crops. And using a hyperspectral framework we developed at the CCIMI, we can very easily classify not only the different types of crops, but also we can start to work out the crop ages just from a satellite photo, an impossible task using RGB alone. And I hope I have now motivated why we use hyperspectral imaging. And I thank you for listening.